Good evening or good day. My name is Oliver and I work for Wolfram Research, and I'm going to be presenting about PDE modeling today. So PDE modeling and the finite element method that makes some of the PDE models that I'm going to show possible. So I work in the numerics group, and I typically work on functions like NDSolve, ND eigensystem, or interpolating function, basically all the functions that in some way or another depend on the finite element method. And I'm going to present a few things about that today. So the idea is basically to give a bit of an overview of the PDE modeling capabilities of NDSolve. NDSolve is the differential equation solving function that Mathematica or the Wolfram language have. NDSolve is what we call is a super function. That means it covers a lot of different areas like ordinary differential equations, boundary value problems, delay differential equations, and things like that. And today I'm not going to cover all of these things. So I'm really concentrating in this presentation. I'm concentrating on this last part, so partial differential equation solving. And there again, on a subcategory where we have arbitrary regions. So we have a different partial differential equation solver for based on something like a finite difference method for rectangular regions. But here today, we're going to talk about arbitrary regions for the finite element method. So when I say something today that this works or doesn't work, I only refer to the finite element method and arbitrary region partial differential equation solving. It doesn't necessarily mean that another function cannot do this specific equation, just to narrow down the scope of this presentation a little bit. Okay. So to get started, why would anybody be interested in solving finite element problems or PDEs over arbitrary shaped domains? And the thing is that if you look around yourselves, you'll see many things that are just not rectangular. So arbitrary shaped domains are omnipresent, and we'd like to be able to solve partial differential equations over them. So that's one of the main reasons of why the finite element method is popular, because it can solve over arbitrary shaped domains. The second reason why the finite element method is popular is because it can solve a large class of PDEs. So we can solve PDEs from, I don't know, heat transfer, fluid dynamics, structural mechanics, mass transport, and things like that. And we're going to see a few examples of those in a minute or two. One thing I'd like to point out is that it's almost always possible to write a solver for a specific problem that's more efficient than a finite element solver or a general purpose solver like NDSolve. But the finite element method is almost always a pretty good choice for specific partial differential equations. So while it's not always the best method for a specific problem, it's always a fairly decent choice for a large class of problems. So that's just a little, to put this a little bit in a perspective. Okay, so let's start discussing a bit what PDE solving is about. So we want to solve partial differential equations, and these come up in numerous fields, in physics and engineering and biology. Everywhere we'll find partial differential equations. To be able to solve partial differential equations, you need basically three things. You need something that defines what the region is, or the object over which you'd like to define or solve this partial differential equation. Then, of course, you need the partial differential equation itself. And lastly, you need some kind of a boundary condition. So the boundary condition is basically something that says what is happening beyond the region you're interested in, beyond this domain that you'd like to solve. And the boundary condition is basically the interface between the PDE that's active in the specific domain and the rest of the world outside of it. That's what boundary conditions kind of are. Okay, so let's look at a specific example. So for NDSolve, or generally in a textbook, you might find something like this. So you have a Poisson type equation. So a Laplace operator, a negative Laplace operator equals to 1. And you'd like to solve this equation over the region is a disk. And then you have a Dirichlet boundary condition. We'll get to that in a second, what that is supposed to be 0 for a specific part of the boundary of this disk. So for x larger than 0. So as the first example, we look at how we'd set this up in Mathematica. So we'd specify the PDE, says minus the Laplacian, u is dependent variable, x and y are the independent variables, and equal to 1, like the problem specification here. We specify that omega is a disk, so that's the domain we'd like to solve this partial differential equation over. And then we specify a Dirichlet condition specifying that the dependent variable should be 0 for all values x larger than 1 than 0. So an x is part of this domain of the disk. So to do this, you then call NDSolve value or NDSolve. It's just a slightly different return value that's given by these two functions. NDSolve, the PDE, and then the boundary condition, the dependent variable, and here you say that x and y, so the independent variables, are part of omega. NDSolve will then solve this this problem, and it will return an interpolating function. I can show you. Yes, let's do that. So let's evaluate that. And here, let's do it again. So now it has returned an interpolating function that contains the solution of this partial differential equation in this disk. And then we'll do some post-processing. So for example, we'll visualize the plot. So we have a plot 3D of that function. And now we can see this is the solution of the Poisson type equation. And we have for x equal larger than 0, we have a value of 0. That's what we specified in the boundary conditions. And the rest here is a Neumann 0 condition, but we'll get to that in a second, what that is. Okay, so this is a really rough rundown of how basically all partial differential equation problems are. You'll set up a PDE, you set up a domain, and you specify some boundary conditions, call NDSolve, get a result, and do some post-processing. So this is really the most simple way to solve partial differential equations. Now, the only thing that changes now is that either the partial differential equations get more complicated, the geometry gets more complicated, some boundary conditions get more complicated, but in essence, it's always the same process to do. Right. Okay. So what type of equations can we solve with the finite element method with NDSolve? Well, okay, so we have this type of a coefficient form that we can solve, and that's a fairly general equation. And I'll get to that in a second again. So we have a second order time derivative with the coefficient m, first order time derivative with the coefficient d. Then this here is it's kind of a diffusion type of term. Then we have a conservative convection term, again, coupled with this gamma. We have a derivative term, a convection term here, reaction term, and the right-hand side. So, oops, the F here, and the right-hand side here. And with this, you can model some commonly known equations. So highlighted in blue is, for example, how you modify this to get a Laplace equation. So in this case, you'd use this C term here, and you'll have F is set to 0, then you'll have a Laplace equation. Or if you do a Poisson, like to solve a Poisson type equation, like we've seen before, the only thing that changes now that F has a value. And in the previous example, F was set to the value of 1. We can also solve Helmholtz type equations. Here we have an additional term now that's a reaction type of term for Helmholtz type equations. Convection, diffusion, reaction type equation. So again, we have another new term here. It's a convection term that's added. A heat equation with the first time derivative, or a wave equation with a second time derivative. Actually, as a matter of fact, we can have any order of time derivative. It's just that these two first and second order time derivatives are the most common ones. Right. So when you look at this equation, you might say, nah, well, it's only just a single one equation. Every example you're going to see today has been done with this equation. Every single example that I'm going to show has been done with this equation. The one thing I didn't yet mention is that we can couple these equations. So we can have 2, 3, or 27 of these equations coupled together. And that's what makes for great power in PDE modeling. And we're going to see examples where we've done that. Okay, so let's move on. Okay, let's look at a Poisson type equation again. Now we'll complicate things a little bit. So this is the type of equation we'd like to solve now. So diff minus c grad u equals sum f. And we have boundary conditions. So on some part of the domain, we'd like to have specified the dependent variable in some way. And on another part of the boundary, we'd like to specify the derivative or the Neumann value of this part. Now, note this expression here reappears, or actually I should say this internal expression here reappears in this case just with a different sign. And this is the normal value on the boundary. Now, this part here is never really computed, but it's substituted with something that we call a Neumann value. That's a Neumann type of boundary condition. So the geometry I've chosen now is something like this rectangle with a half circle or half disc cut out. And this blue part here is where we're going to have this Neumann value. And the red part is where we're going to have a Dirichlet value specified. So let's do that. So the way I specify this region is by calling an implicit region. So an implicit region allows you to implicitly specify a geometry. So here we have from 0 to 5 in the x direction and from 0 to 10 in the y direction, but not this part, which is the disk that we've cut out. And the operator here is minus the Laplacian minus 20. It's just, this is the f value, the right-hand side value that I've chosen. For the Dirichlet condition, we're now going to say, so this Dirichlet condition, the dependent variable u is set to 0 at x equals 0 and y between 8 and 10. So if we go back to this slide here before, we see that's this part here. So we just narrow it down to this specific part here. And for the Neumann value, we just say, so this is actually a generalized Neumann value because it depends on the dependent variable. And here, so it's minus 2 times u, and then again, we specify where this value is active. This is the boundary of the circle, basically. Then, as before, we solve the equation. Let me quickly show this. So what's different now is we had this operator, which is the Laplacian. Let me show you again quickly. Let's move up here. So this is the Laplacian minus Laplacian minus 20 equals to this Neumann value. So that's there. And we specified the Dirichlet condition. And then I plotted a visualization of the solution with the finite element mesh below this. So this is the solution. We'll see here that at this end, the value is actually 0. That's what we specified here. The dependent variable is 0, and that on the disk here that's been cut out is this Neumann value, this generalized Neumann value of minus 2u. Okay, so that's a little bit more of a complicated example. Okay, so let's talk a little bit about boundary conditions. So we have several types of boundary conditions you can specify. We've already seen a Dirichlet condition. That means you prescribe the value of the dependent variable u on the boundary. You say, for example, if you're looking at a heat transfer problem, you say that the temperature, it has a specific value on this part of the boundary. The Neumann value is different. That specifies basically a flux over an edge. So if you think in terms of heat, how much heat is lost through through a window or through a wall or something like that. That's something you'd model with a Neumann value. So the default boundary condition, and that means if you don't specify anything on some part of the boundary, means a default value of a Neumann zero value. That's the natural boundary condition. And that's why they're also called natural boundary conditions sometimes, because this is just, if you don't do anything, this is automatically satisfied, right? Okay. We also have periodic boundary conditions. I haven't shown an example of those yet. And these work that you have some predicates, something this here, you want this boundary condition, the blue one, you want that to be the same as this green one. And this works by every part of this boundary is mapped to this part of the boundary, and the values taken from here are then put back on this part of the boundary condition, which makes for a periodic boundary condition. Okay, so these are the type of boundary conditions that we can have. Okay, so now I'd like to talk a bit more of how to set up partial differential equations. And as we've seen before, we have different types of things that we need to do. We need to specify the geometry or the domain, so the geometry or the mesh, and the PDEs and the boundary conditions. So first, we're going to look at specifying partial differential equations and boundary conditions. And then later during the presentation, I'm going to show some things about how to specify the geometry and generate finite element meshes. So for the partial differential equation setup, we'll have a quick look at the documentation. So let me quickly enlarge this a little bit. Right. So there's a lot of text here. You can read that. That gives an overview of what's available. What I would like to point out is that for specific or a collection of fields of physics, we have more detailed information and predefined operators, and we'll see those in a second. So, for example, we have some things on acoustics. Acoustics PDEs, so which type of PDEs are used in acoustics, boundary conditions, and there is monographs, which are kind of, well, which are actually textbooks with lots of examples and explanation of the theory. Here's another one, acoustics in the time domain, acoustics models and examples. So we have covered, for example, acoustics. We started covering electromagnetics, so there's still some stuff missing. We have done some part of fluid dynamics. It's also not quite complete yet. That doesn't mean you cannot solve fluid dynamics problems right now. It just doesn't, the equation setup is maybe not as easy as it will be in the future version, but it's not impossible to do this. And I'll get into more details in a second about that. So here we have heat transfer, mass transport, multiphysics examples, structural mechanics examples. So let me maybe take like heat transfer. That's something that's that many people are probably familiar with, and walk through that. So if we click on this, this first is a link that's going to take you to a guide page. On that guide page, you'll find all functions that are relevant for heat transfer modeling. So we have a heat transfer PDE component, and then a whole slew of boundary conditions: heat flux value, heat insulation, outflow, radiation, symmetry, temperature conditions, all these type of things. Then there is gonna be a list of monographs about them, and we can have a look at them in a second. There's also, for this case, we also have a verification model. So that shows you that the operators that we have work correctly. And here's a section of models that we have. And lastly, on that guide page, you'll find an overview. And let me enlarge that maybe a bit bigger. Okay, an overview page So this heat exchanger example, for example, is a 2D example. It's a stationary example. It's a coupled example. It uses the heat outflow values. This gives you some guidance of what these examples are about. Okay, but let's look back at so the heat transfer PDE component, for example. So this is the actual reference page, and it has like a summary of the theory of what this operator does, and we'll see examples of it just now. So this is like a standard reference page. You should be familiar with that. One thing I'd like to point out are these monographs. So this is a monograph, let me enlarge this again, is a monograph about heat transfer. It gives a short introduction, and then what it does, it starts by showing what the equation, the relevant equation in this field is. It does the derivation of these equations, where do they come from, what units do they have, and things like that. And it goes on to show many examples, specific applications like a volumetric heat source, what that is, and things like this. So this is what you usually find in a book, maybe, but in this case, the book is included with the Wolfram language, and you can execute it and evaluate examples and make use of the content we have there. Okay, so let's get back to the presentation. The point here I wanted to make is basically, if you want to do PDE modeling, there is a lot of material that we have, and the best or a good starting point is this PDE models overview page. That has really a lot of starting points. Yeah. Okay, so let's look at an example again. So we have a heat sink here, and in this case, I have a predefined geometry that I've loaded into the notebook. And yeah, the first thing I'm going to do now is I can generate a mesh here. 2-element mesh is the function to do that. And this geometry now has two colors. So it's red and green. And the reason it has two colors is to highlight a different way to specify boundary conditions. So all elements that are in this red area will have a different boundary condition than those elements in the green area. It's just a different way to do this. The way this works now with this PDE components is the following way. So we say we have the dependent variable u, it's a 3-dimensional problem x, y, z, and the independent variables x, y, z. And we now specify the thermal conductivity is 232.6 watts per meter Kelvin. And we'll plug this into this heat transfer PDE component, the vars and pars. And now this generates for us the proper PDE component that we need to use. So while you might be able to write this up like for a simple heat transfer problem, it's very hard to remember and write down equations, for example, for, I don't know, hyperelasticity, for example, or complicated fluid dynamics. These PDE components generate the proper equations for you. So you don't have to use them. So NDSolve will work happily without them, but it makes it a lot easier to create partial differential equations. So that's the first point I wanted to make. Right. And the same goes for the boundary conditions. So I have a heat transfer value that I want to specify. Element marker now refers to the one colored region that I've mentioned. So this is element marker 1. And here in the second example, we have an element marker 2 that refers to the other region. So the heat transfer value gets a position where this boundary condition is active, and it gets the variables and parameters, and they're exactly the same variables and parameters like for the heat transfer PDE component. And now we can specify additional parameters for this boundary condition: the ambient temperature, the heat transfer coefficient, to set up this Neumann value. So this is now the Neumann value that's generated for us. So of course you can go ahead and write this down if you know this, but there is functionality that generates these boundary conditions for you. And let me show again, maybe if we quickly go to the reference page. So let me, so this is the reference page of the heat transfer value. Let me enlarge this a bit. And if we look, so I mean, obviously, like for every reference page, there is plenty of examples here. I don't want to go through that, but in the details section, there you'll find all parameters that you can specify. So in this case, we have just two parameters. We use them both. The ambient temperature, it tells you what the default is, heat transfer coefficient, and things like that. That's where you get the information from how to set up this specific boundary condition. That's on these reference pages then. Okay, let's close that. And we have that for all boundary conditions that we have, of course. Okay, here's the second one. It's a heat flux value, and there the element marker 2 means that the rest of the domain vars parse, like for the heat transfer PD component, and the heat flux is set to 1000 watts per meter squared. Right, and then again, it's calling NDSolve value. So we have the operator. Now we can quickly go back to remind us what that was. So here, this is the heat transfer PD component that generated the PDE for us. Let's go 2 slides forward. The two boundary conditions, the dependent variable is U, X, Y, and Z is the mesh. And then this is now the solution. I haven't really shown how I've visualized them. I think there's other presentations that are more focused on visualizations, but this is the outcome of the simulation then. Okay, so I have a question. Let me quickly see. So the question from Lou is that the PDE solver from System Modeler? No, this is not the PDE modeler from System Modeler. This is a completely different PDE solver. So this is basically, what I'm showing today is geared towards finite element analysis. This section of NDSolve is geared towards finite element analysis. System Modeler is a product for doing system models, like lumped models, like you might have electrical circuits that are coupled together, and doing these kind of simulations. So they're a bit different, but this is a different solver than System Modeler. So the next question, is the Landau-Lifshitz-Gilbert equation model included? Honestly, I don't know. But the question, I mean, the thing is, if you, so let me put it that way. There is no specific Landau-Lifshitz-Gilbert equation PDE component. We don't have that. If you can transform your partial differential equation into this form, then it's supported. Sometimes it may take a bit of thinking, but these are usually, this is usually a fairly general PDE. And the reason why I can say that with confidence is basically, this is a second order spatial derivative. This here is a first order spatial derivative on this operation. Again, a spatial first order derivative on something that doesn't depend on the dependent variable. Again, a first order spatial derivative, different because now the beta is outside of this gradient, and here it's basically the divergence acts also on this alpha. And here is the dependent variable without any derivative. So what this means is basically for up until second order in space derivatives, any combination is possible. So that covers it. If you have higher spatial derivatives, then you need to become creative. So then you might need to split up the PDE in a system of PDEs or something like that. And then there's a question, if there, I hope I understand correctly, if the Landau-Lifshitz-Gilbert equation is planned to be included, not at the moment. So I mean, you can contact me after the talk and we can discuss this in more detail if you want to. Okay, let's move forward a bit. Let's go back to the heat equation model. Right, so this is the heat sink that we've just looked at and the solution. Okay, here is a second example, and this example is from solid mechanics. Right, what's different now? So solid mechanics is basically we want to compute deformations of objects, and this is a system of partial differential equations. So basically the equation I've showed above, this coefficient form, now we have 3 of them. What we have here is a crankshaft, and what we're going to do is we're going to hold this fixed at this end and at the other end. And then we have some pressure on these 2 parts of the crankshaft in the downward direction, and we're going to see how this thing is gonna deform. Okay, so I create a mesh from this. This has 180,000, almost 180,000 elements. I've used a first order mesh. We have up until second order, but I'll get into more details when I talk about the mesh generation. And now the parameters change a bit in that we have U, V, and W. So now we have 3 components, 3 dependent variables, and the independents are X, Y, Z. So we have a 3D object. And Young's modulus is 10 to the 9, and Poisson's ratio is 33/100. And now it's the PDE modeling. So we use a solid mechanics PDE component that's going to generate the actual PDE. We say solid boundary load value. We specify the region where we want this. So we have 2 regions there, bars and pars. And then we have a pressure of 1,000 1,000 pascals in the negative Z direction. And then we hold this object fixed at everything smaller than 0.1 and everything larger than 980 millimeters. We solve this equation, and in this case, I've included the time. So this takes about 5 seconds to solve. And yeah, it's again, we specify the PDE. Vars is just a dependent variable, so U, V, and W. And the independent variables are part or omega of this or element of the mesh, right? And this is the visualization. So what we see here is a plot of the total deformation. So all deformation in all directions added up, squared added up in the square root. And that's a visualization plot of this. In gray, you see the original crankshaft, and in the colored object is now the deformed object. Okay, I have another question here. I thought that the heat equation used thermal diffusion as the constant. Oliver's model is using thermal conductivity. Why isn't thermal diffusion used in Oliver's model? So I'm not 100% sure I understand the question 100%, but I think we're talking about the same thing. Thermal conductivity. So let me go back to that example. No, one more slide. Thermal conductivity. So if we go to the reference page here, make this a bit larger. Oops, so no. Like this. So we can look at this. So these are the parameters you can specify. A heat convection velocity. So that's if you have a flow over the object. But so here we have the thermal conductivity. So this is the thermal conductivity in watts per meter Kelvin. That's I think, if I understand your question, that's the same thing as the thermal diffusivity. But if not, maybe you can give me another message and I can have a look at that in a second. Yeah. Okay, let's close this again. All right, let's move forward a bit. Okay, so now we have talked a bit about the PDEs and the boundary conditions. And the next thing we're going to look at is the geometry and mesh generation. That's an important part, of course. So you can either import a geometry or mesh. So for example, we can import step file format, which is a common CAD file format, STL, DXF, and a few others. I don't even. So the import reference page will have an exact list of what can be imported. A second approach is you can create your own geometry. And one way to start is with this guide page is the derived geometry region. So let me enlarge this again a bit and make it full screen. So Boolean operations like region union, region intersection, region difference, things like that can be used to build up geometries. We've seen in the presentation before the implicit region. That's another way to set up a geometry. Yeah, so, and then here's a list of operations you can do on these things. So that's one way to set up a geometry. What I'd like to do today is to look at something that's maybe not so well known. So the Wolfram language and Mathematica actually ship with a CAD engine, with a CAD engine. And we have a link to OpenCascade, and that's included in every version of Mathematica. Well, every recent version. I think we included in version 12. So here's the link to that. So it's a tutorial on how to use OpenCascade, and we're going to look at a few examples just now. Okay, so I'm not going to dive into that just yet. So here's an example. So this is a little bit of a lower level interface than what you might usually expect from the Wolfram language. But again, this is also yeah, it allows you to really get your hands dirty with geometry generation. So it has lots of features that are not in the system context, but they are in their own context. So we load this package here, needs OpenCascade link, and what you do then is, for example, we have this graphics primitive ball, and what we can do is we can convert this we use OpenCascade shape to make an OpenCascade expression. So with OpenCascade now, the CAD engine now has a representation of this ball. We can inspect the type. So it tells me this is a solid. And we can convert this OpenCascade surface mesh to boundary element mesh of this shape that we've created. And that's going to generate a boundary element mesh, which is the basic type that we use for the finite element mesh. And here is a visualization of that wireframe. Now, that's not particularly spectacular to convert a ball to the OpenCascade and back again, basically. But that's the basic workflow. There is nothing more than that you basically need to know. You can now use Boolean regions, all sorts of things to create geometries. Now, okay, so let's look at a few examples. I mean, we've already seen this primitives, like a conversion of ball. I mean, and I think there's all 3D graphics primitives can be converted to OpenCascade. So cones, cuboids, cylinder, ellipsoid, filled torus, hexagon, you name them. They're all there. So that's possible. We can convert surface primitives like splines. So here we have a B-spline surface that's specified, and we can convert that to OpenCascade and look at what it looks like. So this is after the boundary has been meshed, but we can convert it to OpenCascade and work with that. There is surface meshes. So this is an implicit region. I've generated a boundary mesh and converted this to OpenCascade. And you can work with that in the CAD engine. That's fine. Operations sweeping or lofting is very interesting. So this is here we generate a loft. So that means we have 3 base objects like this triangle here, a circle here and another triangle here. And now we'd like to generate the surface that goes through these three objects. That process is called lofting. So here we see that now. So this is just the surface now that's open. You have functionality to also close these lofts. So build solid true. Yeah. So generate me a solid. And then here is the closed version of that same thing. So lofting works. Again, as I mentioned, Boolean operations, fillets, chamfers, deshelling, defeaturing, all these kind of things work in Open Cascade. And that is a really powerful engine, especially for 3D geometry generation. Let me close that and go to the next slide. Well, all right. So here is an example. So this helical bevel gear, and that's been completely created in Mathematica. So what we have here is a curved gear, some gear teeth at the back, things like that. And there's an entire, again, there's a tutorial. It shows you how to generate things like this in Open Cascade with all sorts of tips, tricks, how to do things like that, lofting again, and things like that. So that's maybe another thing if you want to look at if you're really keen on generating geometries in 3D. Okay. What else? Okay. Mesh generation. So the geometry is one part. Once we have the geometry, we'd like to generate a full mesh from this. And for this specific topic, the go-to tutorial is basically the element mesh generation tutorial that has, again, a lot of features of how you can generate meshes in many different ways. So let's look at a few examples. So first off, you can manually generate a mesh. That's not a problem. So you say 2-element mesh, you give a couple of coordinates, and you say the mesh elements are triangle elements. So in this case, they are linear elements. And you'll generate that mesh, and here's a wireframe of that mesh. And you can use that mesh in NDSolve to solve your PDE if you want to. So that's a manual way is possible. Then we've got symbolic regions. So here, like we've seen before, like toDisk is generating basically from the symbolic expression a mesh. An implicit region, that's maybe a bit more complicated. And I mean, this is a purely mathematical description. So it's going to be very hard to generate a mesh of this math expression in other software. So, but you can do this with Mathematica. That's possible. I mean, what else do we have there? Right, so here's an annulus, so we can have holes in the region, of course. That's not a problem, sure. Oh, here's another interesting way to do. So we can, so here I've generated a mesh from an annulus, right? Now I can extrude that mesh into 3D by using the function element mesh region product. So this is the mesh from above, and now I multiply this with a line element, or a line element mesh, basically from 0 to 1. So this is a 1D mesh, and this is a 2D mesh, and I can get a 3D mesh. So this is the 3D mesh. So now it has 2 layers, and you can improve, add more layers if you want to. That's not a problem. And these are prism type elements, so that's also possible. Yeah. Another thing that comes up from time to time is graded meshes. So graded meshes have. Do I actually have a graphics here? Oh yeah, here's one. So graded meshes are a way to have rectangular regions meshed with an emphasis in specific area. So these are rectangular regions. So if I call this function toGraded mesh, it's going to return me a 1D mesh from 0 to 2, alignment central, and for example, mesh. Oh no, I'll need to change that. Mesh region. Oops, mesh X. So there you see, let me enlarge this a bit. You see The alignment is central. So this has a concentration of nodes in the center. There you have it. Okay. Here is a second one, and that's one of the two meshes I'm going to use just now. Here's a second mesh. Again, I have an alignment central, but this time I have an edge count of 50. Let's copy that. Put that in here. And change that. So now you see the mesh is denser, of course. We compute the region a product, and here is the mesh for this specific area. So if you have something that has a lot of activity in this area, then such a kind of a mesh is useful. So if you change that, for example, go to right, then the concentration is on the right. We leave that the same, and to do another product here, visualizes. So now this concentration is increased on this side. So that's what you can do with graded meshes. Very useful, especially like for convection dominant PDEs where you have some action somewhere on the boundary or some things like that. Then these are really useful. One thing we're going to talk about in a little bit is we can, of course, also generate multi-material regions and meshes. That's possible. We have PMLs. So PMLs are basically, if you want perfectly matched layers, if you want to have equations that have interaction with the boundary and that dampen out some kind of a wave that's going out of the geometry, PMLs are used to make this happen efficiently and at a high quality. So we can have these type of meshes. You can generate meshes from images, from contours. There's, it's endless what type of mesh generation you can have. Okay, yeah, so good. These are the main functions that we use for finite element mesh generation. Two-boundary mesh, again, documented loads of examples. So this has 52 examples. Two-element mesh is the second one. So this has almost 100 examples. So the difference to boundary mesh is generating the surface mesh, and two-element mesh is then generating the full mesh, the full object of this of the geometry that you have. To graded mesh, we've seen examples, and then there's an entire tutorial on element mesh visualization. So very simple examples, simple meshes, how you address specific parts of the mesh, how you add markers. So these elements have the same markers, these have the same markers, then you can have a PDE that, and we're going to see an example that has a different behavior in this area than in that area, and you want to visualize that. So things like that are possible. Right, so yeah, have a look at these reference pages. They have plenty of examples. Okay. And here's a little gallery of examples. So this is a piston, and the coloring here is actually to highlight different areas that you can address with different boundary conditions. Here is so I've used the geography information of the island of Pico of the Azores, and use that as a contour to generate a mesh that's going around this. So if you want to do, I don't know, some geometry PDE modeling, that's certainly something that's interesting for you. The crankshaft, we've seen that before. So here's a mesh of that, and here's a 3D version of the graded mesh. So there's just a few images to show. Right. So let's get back to this partial differential equation that we've seen before. So these are coefficients that these PDEs can take. These coefficients can be nonlinear. They can depend on time. They can depend on the spatial variables. So yeah, they're fairly flexible and fairly general. This example here is an example from electrostatics, a shielded microstrip. So we have an object here that has a small cutout, and here I've used Boolean operation to generate the geometry. And what we're going to do now is move on. The PDE now has, so this is a Poisson type equation again. And this coefficient here, the epsilon r, is dependent on the independent variables. So it's spatially dependent. And the expression I have here, if the y coordinate is smaller than some variable I haven't further specified, then it should use this coefficient. And if it's larger, then it will use this coefficient. And the operator now is like the inactive divergence minus this function, this if statement, the dependent variable, and then minus some constants, right? And the boundary conditions are u is set to 0 on y equals 0, x equals 1, and y equals 1. And we have a Dirichlet condition 10 to the 3 at this part of the domain, and we'll see in the solution just now. So we call NDSolve operator, no Neumann values, and the right-hand side is 0. So the Dirichlet conditions, and this is the solution. So what you note now is that the solution has a small kink here, and that's because the material parameters have changed in the different regions. So this SH is actually set to this line here. And there, the if statement knew what to do when it was evaluated in the different regions respectively. Okay. One thing I'd like to point out is the automation that's happening. Nowhere, I mean, let's go back to this. So this is the region difference that we use to generate this thing. This object. There is no line here, no division or anything like that is here. But in this case, NDSolve was able to figure out that there is a material discontinuity between these two regions. Just because it could analyze this if statement, it automatically introduced this additional line. And then this is actually the boundary mesh that the geometry is generated from. And the reason is that the finite element method works better if the evaluation of this function happens only within the element, if the element doesn't transition material boundaries. So that's something that happened automatically. Now this happens, this automatic introduction of this boundary material or this material separation can happen in many cases, but not always. And then you can always add it manually if you want to. So there is some automatic functionality here as well that I wanted to point out. Okay. So what kind of solvers do we actually have? So we can solve linear and nonlinear stationary problems. We have both iterative and direct solvers. The default solver is the Paradiso solver. That's fairly efficient. We can solve transient or time-dependent problems. We have solvers for frequency dependent problems, parametric equations, and eigenvalue solvers are available. So this kind of covers, I think, all of the commonly used solver types. Okay, here's an example of a transient problem. Or maybe let me quickly have a look. No. Okay, so here's an example of a transient example. So what we have here is a duct that has cooling pipes inside, and we'd like to model it. So we have a hot fluid inside and some temperature outside, and some cooling fluid is flowing here, and we'd like to model the heat distribution in this pipe. Because this has a symmetry, we only model part of it. So this rectangle, this region here that's highlighted in blue is actually the simulation domain. And I've expressed this as an implicit region. if you don't like implicit regions, that's not a problem. You could very well use Boolean operations to generate something like this as well. That's not a problem. So here's one way to do it with an implicit region. So now I have a Neumann value, and to make things a bit more interesting, I made this Neumann value time dependent. So for all simulation time, we're going to have for smaller t equals smaller 10, we have minus 100 times t, and then we have a fixed value of 1000. And this is where the part is active. So this is in the inner circular part in this cooling part here. Right. Then we have a Dirichlet condition at the inside and at the outside. The inside, the liquid or whatever is inside is 200 units degrees if you want, and 15 at the outside. So what I've done here is a time-dependent operator. So now it depends on time x and y. That's this part here. What I'm doing now is, so I'm going to solve a time-independent problem at t0 to get an initial guess for a starting value. So the initial condition for the time-dependent problem can be found in this case by solving a time-independent problem. You could use other things here. It's just, I just wanted to show different approaches. It's not specifically necessary to do this. For time from 0 to 25, mesh we've generated above, the boundary condition here, I've added the time-dependent derivative ut x and y, comma dt means the time-dependent derivative of the u variable. Neumann value, Dirichlet condition. Right, so no, I think there's more on this slide. Right, there's a solution actually. So here you see now a solution. So you just see, so this is the temperature at the inside is 180, 85 or something, and going to the outside is 25 here. So and you see how this temperature changes with the amount of flux that's going over this edge that I've made time dependent. Yeah, okay, so that's just to show you a time dependent problem. Right, and there is a solution plotted into this pipe thing. Another common problem are eigenvalue problems. So in this case, we have our PDE coefficient, our PDE, our coefficient form of the PDE, and solve that equals to lambda u, and lambda is the eigenvalue that we are looking for. So here's an example. We have a Laplacian of u minus the Laplacian of u from 0 to pi, and we want 4 eigenvalues. When we call ND eigensystem is the function that does this. The first eigenvalue is almost 0, 1, 4, and 9. And here are the corresponding eigenfunctions that match the eigenvalues. So that's how you'd solve an eigensystem type of problem. Okay. Right, so here's a second example, 2D example again, negative Laplacian. Now we have a boundary. So the previous example, this one example was just the equation. There was no boundary condition. Now we have a Dirichlet condition. So everywhere on the boundary, that's what you say when you say true. This means everywhere on the boundary, the dependent variable is 0. We solve the negative Laplacian over disk, 6 eigenvalues. The eigenvalues and the eigenfunctions are visualized here. So these are the 6 eigenvalues and eigenfunctions for this specific setup. Right. So this is here. Here's an example where we use an image. So what we have here is this mini car that's been chopped in half. So someone cut this in half, and we're just going to use this for an example. So this is the image we're going to compute eigenvalues for. So we used the mask tool and generate a boundary graphic. So this is now the contour of this this thing inside. That we use to generate the boundary. we boundary discretize the graphics. So this is now a boundary discretization. And we can now use that as a region for the geometry for the eigensystem solver. So we solve a negative Laplacian again. That gives us the values and functions. And then we can visualize this. So there you have one of the solutions plotted into the mini. So this is, I mean, it's of course it's a toy example, but I think it looks quite nice to do that. Okay, right. Let's see how much more material I have. I think a little bit. No, so that's it. That's basically all I wanted to cover today. Let me give you a brief summary. So we can solve nonlinear variable coefficient transient systems of PDEs over arbitrary regions. We can do this in 1, 2, and 3D. My name is Oliver. You can reach me at wolframresearch.com. I thank you for your attention. I'll answer questions just now. If you're interested in an internship or something like that, send email. We're always looking for good people. So if you're interested in working in this area, let me know. Okay, let's see if there's more questions. Oh, Craig Carter. You've written them, it appears. Okay, so Craig asked, he says that I've written a lot of material in the documentation. Are there any plans in the works to write a book that collects the documentation and perhaps more into a book, perhaps like Able? Yeah, yes. So these plans exist. Yeah, so people have asked me that before. What I'd like to do before doing that is I'd like to finish. So right now I'm working on fluid dynamics. So we've seen like the heat transfer examples and the solid mechanics example. These all have fleshed out monographs and extensive reference pages and things like that. And I'd like to do that for fluid dynamics next. So we can solve fluid dynamics today, right now, but you'd have to have the knowledge how to do that yourself. So you know how to set up the equation. There are some examples in the documentation now, but I'd like to bring this up to the same level of functionality like the other areas that that I've shown. So once the fluid dynamics is done, a colleague of mine is working on electromagnetics right now. So when these two fields of physics are completed, then I think we'll probably start looking at writing books and getting this out in a different form than the documentation. Right, so good question. Do you have any examples for the green function? I don't, but the symbolics group, they have plenty of examples for the green function. They make use of that all the time. So that's maybe an area where you should look for things like that if you're interested in the greens function. Okay. Right, so if there aren't any other questions, then I'd say we halt here. I thank you again for your attention and happy PDE solving. Yeah, right. So I think we can conclude now.